Okay, so good morning, students. Today we'll be working on question answering based on you could say, a close-ended question answering in which you have some kind of paragraphs and you try to ask some question out of this paragraph, right? And I guess in this tutorial, you will learn a lot more about Huggingface, APIs, and tokenizer, what it returns, and how do we actually manipulate, and hope it will be useful for other NLP tasks as well. So today we will have to do, we will load the data. We will do some pre-processing, and I'm going to demonstrate something. And once you understand that, then I will have some functions that we can use right away. And similarly, we're going to demonstrate how do we actually compute matrix in this kind of task, right? Data loaders is very typical thing that we usually do. Model is just loading a bird, so very, very simple. Training, once again, is mostly the same code that we are very familiar with. So, and inference is simply declaring a pipeline. And this is exactly what we want, right? We have something called context, which is the paragraph that we have information, and we can ask some question, right? Based on that, we hope that it can answer this three words, right? Which it can, right? So yeah, so without further ado, why not we begin right away. So the first thing we will do is load the dataset, and we're going to learn this task together. By the way, even though this is a very specific task called squad, I think it shares a lot of similarities with different tasks, right? So make sure that you can also see that and generalize your knowledge to other tasks. All right. So that is the task we will be using. It's called Squad. It's by Stanford. So it's a very popular data set, I think in around like 2016, 17, 18. And now we can actually take a look at the data sets. And as you can see, it seems like we have ID, title, context, question, answers, and there's a training and validation set, right? So why not we try to take a look at some of them, right? So we're going to do train, and we're going to just take the first one, and let's say the question, right? So if this is the question, then what is the paragraph that we are given, right? And it's basically a very, very long context, so we have to deal with this too, but later on, right? So, but anyway, this is the paragraph and this is the question, and based on that, we can actually know that the answer is nothing but give me 1 second. I think it's answers, right? So basically that's it. So it gives it returns you the text and the position in which it starts, right? Which is 515. I guess is let's try this, right? I'm not sure this is gonna work. Maybe let's take that much, right? So you can see that this actually come from roughly that, right? So how do we know when the answer end, right? Well, we just take the length of this guy, and plus with this this position, we should be able to know the full answer, right? So that is the idea. Great. So I think we are kind of okay already with the answers. One thing why I want to point out is that So let's look at the validation sets. Validation and answers. Right. In this case, you can see that validation is quite different from train. That is, there's a 3 answers actually. And if I change it to 2, you can see that you can have 3 different answers. So validation and train is quite different. The only reasons why training has only one is easy for training, but for validation, we want to make sure that we give some slack to the model that, hey, you have three ways you can answer, and hopefully you can answer one of them, right? So that is something I want to point out. Otherwise, I think that's it for the loading data. All right. The next part is pre-processing, and I'm just gonna hide this first. Maybe let's say code that we already written. All right, so I can close this. Now we can start pre-processing. Right. So first of all, let us do tokenization. So import abstract objects called alternative tokenizer, model checkpoint equal to bird base case, and tokenizer is equal to auto tokenizer dot from pre-train model checkpoint. Great. I think that's it. And now we got a tokenizer, right? And of course, deep learning is fun, right? That should give us a very nice, of course, if you wonder what is this, right? We can always input IDs, right? So this is that. And we can now do tokenizer.decode of this, right? And we can see that this is actually what is tokenized. But anyway, first of all, we want to make sure that our tokenizer is fast, right? And it's true, so that things can be done very quickly. Yes. So so let's take a look. How do we actually send our input to the model, right? So in this case, we're gonna send the context concatenated with the question. So that is how we're gonna send. You may say that why don't we send them separately? And that is impossible because usually the model expects just one input, right? So the question is, how do we send the context and the question together, right? And the answer is simply just concatenate them with a separator. So we can do inputs equal to tokenizer, question and context, and we can now take a look at the inputs, right? It's not so clear what this is, so we can do tokenizer.decode inputs dot inputs ID. Okay, so you can see that the question is separated by a separator, and this is the context that we have. All right. But there's one problem, that is our context is simply just too long, right? And there could be some problem like maximum length that we set, right? So that is something that we have to consider later on. So here, in fact, we're gonna do differently. All right. So we're gonna chop the context into pieces, right, while still mapping with the same question. All right. So you can say that in one question, we can have maybe multiple version of this, right? Simply, we want to to make sure that the context is not this long, right? Okay, great. So how do we do that? Well, we can do something like this. Inputs equal to tokenizer, right? So previously we just sent in the question and the context, right? So in here, we're going to do something different. We're going to send that max length is 100, right? Which means that the whole, everything here, we just want 100. And we want to truncate, we don't want to truncate the first one because the question should be complete, but we want to always truncate the second portion after the separator, which is the context, right? So we can use something called only second. All right, and stride equal to 50. So what is this 50? It means that if you chop them, if you chop this context, maybe you chop until if this is 50, if this is truncated, then you want to overlap maybe 50, something like that, right? So that is stride is basically the overlap, and we also want to make sure that it return. If you chop them and if you don't set the overflowing tokens equal to true, then you would just chop one and you cannot get the remaining tokens. All right, so make sure you set it to true, and then we can now enter this, and we can actually take a look at this, right? So we're going to say forward IDs and inputs. Input IDs, and we're going to do print tokenizer dot decode IDs. All right, so you can see that now we have a full set of input IDs instead of just one input ID. Now we have four, right? Each of them is repeating the same portion, but each of them has equal length of context, right? So and the overlap is basically 50. Of course, the first three probably the length is 100, but the last one is probably not because they are the leftover. If I'm not wrong, yep, you can see that this is probably not 100. All right. So now we have some problem, right? Because originally the start we got something called start position, right? Sorry, and now we have to map that to this new set of format, right? So like I said, using Huggingface, usually you don't have much problem in training, but you have a lot of problem in pre-processing and preparing the data to input into the model. Great. So now we can have that. I would change something slightly, and that is coming here. We're going to say return offset mapping equal to true. And what is this? Is basically it would just tell me that which word, each of the word, what is the beginning of the character and the ending of the character. I can show you in very quick manner. All right. Great. So that's good, right? So let's take a look what is returned by this inputs. All right. So definitely we got input IDs. Okay, I'm not sure we can do something called keys. Okay, so we have input ID, token type IDs, and attention mass and offset mapping and overflow to sample mapping. So let us understand what is this overflow to sample mapping, right? And they're gonna answer only 0, 0. Basically, what it say is that all of this actually comes from the same sample, which is 0, right? So this is what it is. And you may say, what is the purpose? Well, sometimes you want to send as a batch, then you want to know that, okay, you chop them up once you chop them now, how do you map back to which sample it actually belong to, right? And why do we want? Well, sometimes we want to know the answer, like what is the answer. So we just go to the sample number and get the answer, right? So this is that. Now take a look. Let's take a look. What else we have here? Okay, we have offset mapping. So let us try this. All right, and maybe we can try 0. All right. So what is this? Is basically it describe. Okay, first of all, 0 means the first sample, and 1 is basically for the second one and the third one. And if I do 4, probably there will be errors. Yep. And 3 is basically the third sentence, right? So what does this number tell us? Well, it just tells us that this guy is there's no offset, so it's 0 to 0. And this is the first character until 2. This one is 3 to 7, 4 characters. This one is 8 to 11, and so on, right? So this is a useful thing because it will be very important when we try to find where's the answers, all right? So this is actually quite important for our case. But anyway, I'm gonna just uncomment it to make sure that it's not too long right now. All right, so I guess that's it. And by the way, just to show you this overflow tokens, why not we change something? All right, so we're gonna say that we're not just gonna use one question, right? So currently we're using 0, right? So why not we use something like 2 to 6? 2 to 6. Yep. All right, and okay, we got some problem. Okay, now because we have a lot of input IDs, now we have some problem. That should solve the problem. And now we can do the tokenizer as a batch. And of course, this is 0, right? And but anyway, just give me 1 second. I will be back and just clear this cleanly. All right, give me 1 second. All right. So now I just do some cleaning. Basically, I did not change anything. I just want to go through quickly to make sure that I did not make any silly mistake. So context and question is basically we now have 2, 3, 4, 5. So we have now 4 questions here, and this is just an example. And now we send them all in batch. And you can see that this overflow to sample mapping is very nice, right? It chopped the first question into 4 chunks, the second question into 4 chunks, the third question into 4 chunks, and then the last question, the fourth question into 6 chunks, all right? So you can see that this overflow to sample mapping is very, very useful, right? Great. So now I want to, we have to make sure that we can deal with how do we actually map the answer to all these chops, right? Because we need to realize that now some of the chop one doesn't really have the answers, right? Well, why some of them have, right? And there's also a problem that maybe we chop at the right of the point in which it contains half of the answer, right? So that could be a problem. So we actually solve the context length problem, but we actually introduce another problem, right? So why not we try to fix this problem together, right? And this is going to be just slightly difficult. All right. So firstly, we're going to do answers equal to raw data sets trained. And this one is the same as what we have do. So just to make sure that if everyone is following, right? So we have the answers. So we can type the answers, and you can see that basically we only have 4 answers, right? But they are chopped into, so all these 4 questions, the answer is basically this. And we don't know this 279 whether it's in which one, right? So we have to we have to do something. And now we have to do start position equal to, so we have to take note where's the right real answers, and positions equal to that. And now what we're going to do is for I offset and enumerate inputs offset mapping. All right. And so basically the first thing we want is sample index, right? So we want to know which sample this is we are looking at. Flow to sample mapping, right? And we are looking at I, right? So we're going to actually print sample index, and we're going to break this, right? So we are actually working at this one right here, right? And of course, if you want to print the offset, is welcome. And the offset is basically this is the offset for the first sentence, right? So basically it say that this one start at this point, etc. Maybe I should print it out, right? So I'm gonna print. Okay, give me 1 second, right? I know there's a lot. It's not easy to get it, so we're gonna do that and make it very clean, nicely. All right, and next thing we want to do, maybe we can print like point out inputs, right? And we're going to put input ID and I. All right, and yep, I think that should be it. Okay, give me 1 second. All right, so this is the sentence, and it's not so readable. So why not we change a little bit? Tokenizer.decode. That's okay. So yes. So basically, what this guy does is this one is basically the position of this one. 0 through 3 basically is this one, and 4 to 12 is basically 4, 5, 6, 7, 8, 9, 10, 11, right? So it's basically tell us where is the position of each of the word in that sentence. All right. So that is the offset. The next thing we want is we want to know the answer, right? So answers sample index, right? We can actually print the answers. In fact, when you actually do this, you don't really want to print so much, but so we got the answers that for this question, the answer is basically the main building, right? And then we can do the starting character equal to answer start 0, right? And the same is end char is equal. So we basically we get this guy, and we also want to know when it ends, right? Which is basically plus the length of this one. So what we're gonna do is we're gonna plus this one plus the length of answer x 0. Yep, I think that's it. So now we have, let us try to print this, right? Start character, and why not we print the end character, right? And okay, great. So now we got the position of the answers right here. Okay. Now we want to find the answers and where, right? So this is the question, and this is the context, right? So we want to actually find that if the answers is in the context, we're gonna give a label to this guy, basically the starting point and the end point, right? Of this whole sentence, right? According to the index. But we don't want to look at the question part, right? Which is gonna save us a lot of time, right? So how do we know that which one is the question and which one is the answer, right? In fact, there's something called sequence ID, right? So let me just quickly print them out. So it's called sequence ID equal to inputs dot sequence ID I, and I can actually print sequence ID. All right. So if you look closely, it's basically say that this is belongs to none, and here is belong to the sequence 0, which is basically the question, and then the rest is basically the context. So the context start with 1, right, and is quite long, right? So using this, we can say that, hey, please only check on the index 1 and keep on finding this this answer, right? And if the answer is, if we got both answer, then we should label that as an answer. If it's chopped, then no, it doesn't contain the answer, so the label is still 0. If it doesn't contain both, then also 0, right? So that is like the way of thinking. Yeah, this one is a little bit difficult, but yeah, once you get a hang of it and print like me, like just line by line, it should be okay. So now what we can do is start with the beginning, right? And we can say that y sequence ID IDX is not equal to 1. So that means that it's not the context part. What we're gonna do is we keep on finding this, and once we add, it will just keep adding until we know that, oh, we found this, and this is the position we want to know that this is actually the start of the context. So we're gonna do context start now is basically equal to this index. Similarly, we're gonna do the same for it. Wide sequence IDs IDX equal to 1, right? So you can just keep reading until the end, in which you're gonna have none, right? So that is probably designate the ending of the context. And finally, we're gonna say context n equal to IDX minus 1, all right? Because once you reach there, we should go back, right? Great. So of course, we can print context start and context end, and just take a look. That is kind of correct, right? So it's 17 and 98. So by eyes, I can see that this is probably 17, and that is 98, right? And it makes sense because the whole thing here is 100, right? Great. So now we are doing great. Hopefully you guys are following along. Now we have to keep the label, right, to our chop context All right. So the idea is case one, if the context does not fully, or basically does not contain it, right? Does not fully contain the answer. Label is 0, 0. But basically, the starting position and the ending position is basically null. Otherwise, is the start and end positions of that token, right? So we also need to count this, if I'm not wrong. Yep. So now, what we're gonna do is we're gonna say if offset context start 0 greater than start chart. So if it's still going on and offset context end 1 less than end chart. So basically we are looking at each of the word, right? So offset basically contains like each of the word, and we're going to start with basically this word first, which is architectural. So architecturally could I don't know which one, but it could start at like 013, right? So the so if 0 does not contain the start character, we move on, and if this is less than the end character, we move on, right, etc. And we keep finding where is our answer, right? So this basically saying that if it doesn't contain the answer, we just say that start positions, sorry, dot append 0. So this is, we're just gonna keep the label as this, and then it will just repeat to the next sample accordingly. All right. Okay, and positions. Okay. But what if we found it, right? Then what we can do is else idx equal to context start, and y index is less than equal to context end. So we make sure we are not moving until the end, and offset index. So beginning with the context start 0 is still less than equal to the start character. We keep searching, right? idx plus equal to 1, and then finally I think we find the exact locations of that word. So we're gonna, of course, once we found that, we have to go back by 1, and similarly we're gonna do the same for this. So let me just kindly copy this to save a lot of time. So this is n, right? And this is gonna be start, and the last one is greater than equal to n chart. I know this like I'm doing this in my head, but just look at this slowly, and it will make sense. All right. And then yep, and then this one should be n positions that append plus 1. All right. So now we finally find the positions, and what we can do is now start positions and end positions, right? So this is basically what we can. By the way, this is not the actual code we're gonna do, but this basically it's just a demonstration of. So we can run this. and there's a bunch of things, right? Maybe I should comment out everything. Give me just 1 second. All right, and now we still have some printing. This one. All right, great. So now we actually have the starting positions and ending positions of each of the questions. So 83, 151, 119, 100, right? Great. So the and if any of them is basically does not contain the answer, it will be basically 0, 0, right? All right. So I guess that's it. Give me 1 second. I will be back, and just let me make sure that I check my code one more time. Give me 1 second. All right. So I check a little bit, and here basically I start at context end, right? And I slowly I should be slowly moving back, right? So here should be minus. And the reason why I feel like there's something awkward is because the starting position is 51 and the ending position is 100. So the answer should not be this long, right? So something must be off. So let me just run my code again. So I just gonna make sure that it's gonna error here. So clear output, restart, run all. And I'm gonna pause my video, and we'll be back once it's reach here. All right, so now we finish writing this code, and it seems like now it makes more sense, right? That the answer is actually like not so long, so like just now. So this looks much better. Okay, great. So now we are able to actually align the thing together. So why not we actually try some and see whether everything is correctly done, right? So what we're gonna do is let's say we take sample 0, and sample index is basically inputs overflow to sample mapping and IDX, right? So how does this look like? So it's 0. And then we can also get the answer. The answer is answers sample index X and 0, right? So we want the answers for this one, and we want the text, right? So we can actually print the answer, and it's the main building. And now we want to get the start positions, right? And we already have this list, right? So we just enter, we know the answer is 83 and 84, 5. So let us make sure that that is actually the case, right? So we're gonna say start equal to start positions index. And if I'm not wrong, that is basically 83. And we're gonna do the same as for n. And that's it, right? Now we can see whether that is actually correct, right? So we're gonna say labeled answer equal to tokenizer dot decode, and we want to get the input IDs, right? So we're gonna say inputs, input ID. Okay, IDX, and this one contain, if we just do this, it contains basically if we talk about this, it basically contains the whole thing, right? But now we know that the answer is basically at 83 and 85. So we're just gonna do start and end. Because this one is actually the is inclusive, so we have to +1. Otherwise, it will exclude this guy. Okay, let me try. Okay, great. So now we we found that is exactly the main building, right? Great. So now we are able to to actually do this. And so this is a quick demonstration, right? But in fact, I have already prepared a code that basically take in each of the samples and do some stream of the question, remove some space. The rest is basically the same code that I just talked to you. Of course, I pop them, but it basically it's the same, still the same, and everything is the same. And it returned basically the start positions and the end positions inside the inputs itself, right? So this is what I have written. So we can run this. Okay, great. And what we're gonna do is basically we're gonna apply this using .map, right? Which we also do this in the previous. So we're gonna say train dataset equal to raw datasets train .map, and we can call this function, right? Pre-process training sample examples, and batch equal to true. And once we do everything, we want to remove all the old columns. Column names. All right. So hopefully everything is all right. And boom, right? So yep, I think we are done now. We can actually take a look at maybe 0. All right, so it's quite okay. Maybe we should take a look at what is inside here, right? So we got input IDs, token type IDs, attention mask, start position, and end position, right? So yep, given this one, the question and I, which contains the question and also the context, where is the answer, right? And in like this, so we can actually already send it into the model and train it accordingly. One thing about the validation. Validation is much easier because we don't really have to chunk the context, because there's no problem with computation. So we don't have to align anything. We just need to find that the answers that is predicted by the model match to the answers that is in the validation set, right? So in the validation example, it's much easier. You still tokenize everything, but you just have to make sure that you have the offset and also the sequence ID, so that you can always map back to what is the answer of this question, right? So that is for the validation set. You guys can take a look a little bit, right? All right, so now because we have this function, we can also apply this the same for the validation set. Yep. Raw data sets. One question you guys may have is like, okay, you did not map the label, so how do it knows the answer? Well, because if you have the sample index, then the answer is basically in the examples sample index answer, right? Basically, in the validation set is super simple. That's why you don't have to actually map the label. So the validation .map, we process validation examples, batch equal to true, and remove columns equal to raw datasets validation column names, right? So we're gonna remove everything that is the old one, right? And I think that should be it. Now we can open the validation, and we can see that in here we just have the question and the question and the context. But how do we know what is the answer? Well, we have the example ID here that is retrieved here. So this example ID can trace back to the original data set and ask what is the right answer. And then you can map it accordingly, right? So that is the mechanism how you actually check whether you're doing correctly. Great. So that is a pre-processing, kind of difficult, but not too difficult that we cannot understand, right? And I hope that there's a lot of things here: overflow, offset mapping. You have to get familiar, but once you get familiar, it will be also useful for other tasks, right? So let me just close this and forget about it. Okay, great. So now we got matrix, and I'm not gonna show this code yet because this is the final version. But before that, why not we try to make some understanding, all right? Please let me give me 1 minute. I need to drink some water and I will be back. All right, so now here this is the last thing we're gonna do from scratch, and then the rest is basically something that is very familiar that we all did. So that is how do we actually create a function that can compute metrics, and then because that is required from the accelerate functions, right? So to demonstrate, why not we create a very small validation set, raw data sets validation, and that's select. Maybe we just want to select 100 examples. Right. So we got 100 raw context question answers, blah blah blah. And then what we're gonna do is we don't have any model right yet because we haven't trained. So what we're gonna do is we're gonna use some existing QA model and demonstrate how do we actually can compute the matrix, right? So we're going to use this distilled score, which is already fine-tuned on this. Distillation is basically a technique that can actually learn from a bigger model, and this is a fine-tuned on squad dataset. Great. And what we're going to do is tokenizer equal to auto tokenizer. That from pre-train, train checkpoint. And then the eval set equal to small. So we're gonna just apply this tokenize, pre-process. So we're gonna say small eval set dot map, and we're gonna say pre-process our validation examples. Batch equal to true, and remove every columns that you have, right? Raw data sets, validation, dot column names. All right. So yeah, we now got actually a eval set that has the offset mapping, attention mask, and also input IDs, right? And input IDs actually contain the question and the context, right? And the example ID actually contain the answer. So we now have to figure out how do we do that. Let's think slowly. We first need a tokenizer from pre-train model checkpoint. All right, so we got a tokenizer. If I'm not wrong, this is a fast, right? And then we can now try set up some simple training, I guess. No, basically we're not training. We just send into the pipeline and get some results, and then so that we can actually do some matrix auto model for question answering. And then we're gonna say eval set for model. We're gonna just simply remove some columns which is not needed by the pipeline, because the pipeline don't know, they don't expect this thing. They just want the input ID and just answer you, give you back the start logics and end logic. So it doesn't expect this thing. All right. So hopefully that is okay, right? And then yeah, we want to also eval set for model dot set format, just to make sure that it doesn't have any problem in the end. Torch. Okay. So now we're gonna do. I mean, I'm using my MacBook. It doesn't actually affect anything, but if you're using NVIDIA, then this can actually be very that is available else torch.device CPU. All right. So now we can say that the batch that we're gonna send it to the model is nothing but for K and eval set for model dot column names dot column names. All right. So this is for each of the column. All right. For K in this one, we're gonna say K eval set for model. Okay. Dot to device. All right. So yeah, basically this is what the model expect, right? It just expect that input ID and the value, right? And then the attention mass and then the value, right? And we are putting the value inside the GPU, right? If we have actually. So then that is the batch. And then finally, what we're gonna do is train. We need to create the training model before we actually send it to this pipeline. So we're gonna say auto model for question answering, not from pre-trained. Train checkpoint. Dot to device. Right? And now we got the train model. Now we are ready to just send this batch, this 100 examples into train model and get the output and try to see how do we actually compute the matrix, right? So with torch.nograd, simply because we are not doing, we're just doing like we're not training. Output equal to train model. And we know that this is a dictionary, right, of input ID, attention mass, because it's only 100 examples, I hope it doesn't take too much time. All right. So, but okay, 10 seconds. All right, great. So why don't we take a look at the outputs, and why don't we, can we do keys? Okay, no. Okay, so here you can see that we got something like loss, stop logits, and logits, right? So yeah, so that is being returned. So now what we need to do is argmax and try to see which one actually has the highest probability, right? And then compute the matrix accordingly. So what we're gonna do is start logits equal to output start logits, and we're gonna put it into CPU dot numpy, right? And we're gonna take a look at this a little bit, right? So it's a series of numbers, seems like, and that shape is so there's 100 examples, right? And there are 384 positions, right? So each of the position in the sentence has a probability, right? That associated with whether it should be that position that is the starting point, right? And then we're gonna do AND logics, the same. Give me 1 second. Okay. All right. And we also have the AND logics. And again, out of all the sequence length of 384, what is the probability that they are and the ending character, right? And then we have the probability across all the length for 106 samples, right? Hope it makes sense, right? So this is samples, and this is like sequence length, right? And each of them basically has a probability, right? So if you want to know what is the probability of let's say the first guy, then the higher the number, I guess, probably this one, there's a very high possibility that this is the AND logics, right? Great. So hopefully it makes sense. Okay, so now we get the starting logics and the ending logics. What we're gonna do is now we have to think a little bit, right? So before that, I will do something like this. I'm gonna do import collections and example to features equal to collection default deck list. All right, so this is basically just a dictionary of list of dictionary basically. And what we're gonna do is we're gonna do feature. Feature is basically for each of the context is chopped into 4, right? In the beginning, right? That is the what I refer to feature. And enumerate eval set, right? So actually we can actually print IDX and also print the feature, right? And you can see that for the first one, the feature is basically the same question. You can see this is exactly the same question here, right? And this is also the same, not the same question anymore. So this 2 is the same question, right? And this all this is just so yeah. So that is the feature, right? And then what we're gonna do is we want to do something like this: example to features example ID dot append IDX feature. All right, so that is what we do, and we can erase this a little bit. Okay. All right, so now we can actually demonstrate how do we actually compute the performance, right? The idea is simply we loop through this features, right, and try to see whether which logics has the highest probability, maybe top 20, and then get the best answer, and then compare with the actual answer, right? So that is like a very big picture idea. So we're gonna do NumPy as NP. And then and best we go to 20. Maximum answer length equal to 30. All right, and predicted answers is equal to something that we want to capture this. Once we have this, then we can send. This is the main thing that will be sent to the matrix. So in the final line, we should have something like predicted answer dot append ID sample ID prediction text It's basically best answer, right? So basically this is what will be sent, and also the best answer is basically equal to the max of all the answers we have. And how do we know which column we take a look? Well, we use this column called logic score, right? So basically we take the best answers based on the highest logic score, right? Okay, great. So that would be the last thing we have. But what is the middle thing? It's a huge chunk of thing, but we can now slowly do this. So for example, trust me, this is the last part, and then once we finish this, we can show this, and it should be done. Yep. This video is slightly long. Right, for each of the example in the validation set, we're gonna say example ID equal to example ID, and we can comment this to out, so we can actually sometimes print them out. So we can do print example ID, and you can say this is basically the ID that is associated with this data set, and it's given by the original data set. It's some kind of unique ID that we don't really have to. Context equal to example context and context, right? And this is the context, and then we can have the answers equal to this one, and finally, once we have all the answers appended, we can call max. So for feature index, so for each of the input ID we have, right? What we can what we're gonna have in example two features of this example ID. So we can actually print all the feature index, right? And we can see that there's a two double entry for this one, and we're gonna do start logic equal to start logics of this feature index, right? So now we get the, remember we have a start logics of all 100 samples, right? Here we are looking at the zero index, right? And logic equal to n logics feature index. And then of course the offsets is equal to Viva offset mapping. This isn't required because we want to this is required to find the actual word feature index. All right, so this is the offset mapping belonging to this sample, right? So this is the offsets, and then okay, why not we just club them together, and then finally we can do start indexes equal to np.argsort start logic -1 to minus n best, right? So we get the best one, the highest one, and we want to slowly in the descending order, right? Dot to lists. Similarly, we're going to do the same, but let me just type np.argsort and logic. Yep. The reason why we need to -1 is simply because it starts from small to big, so we want big to small, so we need to reverse a little bit. It looks strange, but anyway. minus 1 dot to list. All right. So now we got the logic of the start and end with the highest probability of the. Now what we're gonna do is for start index and start indexes. Yeah, I hope that you guys are still with me, but yep, it's slightly difficult, but once you watch my video maybe 1 or 2 more times, then it should be okay. Yep. You should also try to print them out one by one. That if that actually helped. Yep. So the first thing is we're gonna skip the answers if they are not fully in the context. Right. So if offsets of start index is none, or offsets of an index is none, then we simply continue. So we don't count that answer. All right. If the answer, skip answers with length, with invalid length, right? Basically. And in this case, if n index less than start index, it doesn't make sense, definitely. And or if n index minus start index plus 1 is greater than the maximum answer length. All right. So basically, we know that it's not exceed that one, so something is wrong. Continue. Right. And then finally, once we get the answers, so we hope that we should get the answers here, append as text, and the text is nothing but from the context and the offsets of start index zero until, so it's basically this position until offsets n index and 1. All right. So that is basically the answer we have. And the logic score, because it's a logarithm, actually probability, when you add the score you multiply, but because this is logarithm of probability, you just go search, right? Logarithm of probability becomes addition. Yep. Is a start logic, start index plus n logic and index. So you can see that if your probability of the start is very high, but if your n is very low, averagely when you try to find this maximum, it would try to find the one that is like the highest overall logic score, if that makes sense. Yep. And finally, we can take this out. I mean, this takes a long time to code, but it's not actually that difficult. Mainly just you have to be familiar with what is in Huggingface, right? And then now what we're gonna do is we're gonna import evaluate finally metric equal to evaluate.load. Last time we used a sequence eval, right? This time we're gonna use basically the metric defined in Square, right? And first of all, let us take the real answers first. Real answers is equal to sorry, this guy is blocking. is ID. The reason why we need to write like this is simply because the matrix expect in this form. So you can see that in predicted answer, I also have ID and prediction text, right? So that is what it expect actually. And then the answers is basically EX answers. And you may say, what is EX, right? EX is basically, okay, give me 1 second. I think it's a dictionary for it, EX and small eval set. Right, so that is the real answers. Finally, we can print the predicted answers. And okay, we want this prediction text, right? So okay, we don't want this list, so maybe we put 0 and we can put prediction text. All right, and along with real answers and answers, right? So okay, give me 1 second. Give me just 1 second. I will be back. I just want to check that. Actually, it should look very similar, but it's not in this case. Give me 1 second. All right. So just now I did some investigation, and I found that now I can get the answers correctly. Simply, I should have indented here because this should be inside this loop, not this example, right? So I should do this, and you can clear all the outputs, restart and run all. Then you can get the results. Okay, great. So now what we can do is we can show how do we actually compute the matrix predictions. Theoretical. So this is the real answers. Yep, I think that's it. But we have to change this. Okay, it's fine. I think it's fine. Yep. Okay. So give me 1 second, and I will be back just to make sure that I did not make any mistakes. Give me 1 second. All right. So here it seems like oh, okay. So references. Yep. Okay, and you can see that now we got exact match 83 and an F1 score of that. All right, great. So that is how the matrix works. And here I have already created functions in which combines everything, taking the start logits and logits and the features that we chop down each of the context into smaller parts and the actual examples, right? And then basically, this is everything that we have already did just now, right? And then I bundle up into and return the metric. Great. For the rest, I will not actually run them because here I'm defining the data loaders for the train and also for the validation set. Okay. And for the model, I'm simply, you can use any question answering compatible model. But here I'm using BERT. Again, basically, it just add a linear layer on top of the BERT. So and then fine tune it, right? So you can, so this is that. And optimizer is the DOM. And I define the accelerator. And I think if I'm not wrong, I cannot use this one simply because I'm using MacBook right now. So okay, I think I have to insert something. Give me just 1 second to fix this error quickly. All right, so basically I just delete this one and then rerun everything. Now it's fine. Okay, and here it's a scheduler that we did. And I'm not gonna run this code. Basically just log in, define the model, and then just train it, right? And then the validation, of course, there's just gather all the start and ending logics because it's parallel machine, concatenate them into one whole list. This is a little bit strange. Why do we need to actually bound them? I found that the accelerator adds some strain padding, so sometimes you want to just make sure that it's equal to the validation data set exactly. Yep. And then we call compute matrix, and then yep. And finally, we can run the inference. If I'm not wrong, I can already run this because this is already in the model, but I don't remember whether I locked in already. Yep. So yep, seems like it should be okay. It takes a little bit of time, so once it's done, I will be back. All right, so the model is loaded from this public Huggingface places. And what I asked is basically which deep learning libraries is related to transformers. And you can see that it can correctly answer with 99%. Okay, great. So hopefully you learn a lot. It's not exactly straightforward, but feel free to come to this and take a look, right? And I just want to shout out that actually this is this tutorial is basically from Huggingface page. So surely take a look at this page too. Thank you very much and see you in next class. Bye-bye.